Good afternoon guys, and welcome to a little top tips video today whereby I'm gonna use the periodic table to show you what I think is a far quicker and much easier way of working out electron configurations. So as we know, when we switch from GCSE to A-level, writing A-level configurations is a little bit more tricky, because as well as having main energy levels, we've got sublevels, and then we've got atomic orbitals as well. When you hopefully had a look at this in the atomic structure topic, we can also label some extra things onto the periodic table. So we can label groups 1 and 2 as the S block, then groups 3 to 0 as the P block. These elements in here, which we've historically called the transition metals, their more correct title is the D block elements, and then the lanthanides at the actinides at the bottom, which we still don't need to worry about, they would be the F block. Now that tells us the orbitals that the outer electrons are in for that particular element first and foremost. So lithium will have its outer electron in an s orbital because it is in the s block, and because it's in group 1 it will have 1 electron in said s orbital. If we were to look at phosphorus, phosphorus is in the p block, so phosphorus would have its outer electrons in a p orbital, and so on and so forth. Same for the D block, same for the F block. Now, in terms of how we fill the main energy levels and the sublevels that we now need to know, we fill them from the lowest energy, so closer to the nucleus, outwards to the higher energy sublevels and main energy levels as we get further away from the nucleus. And we need to remember the specific order of filling, and unfortunately it doesn't just go the first main energy level S, then the second for S and P, and then the third for S, P and D, and then the fourth S, P and D. Initially it starts like that, but then as we get to the higher main energy levels, we get some overlap of some of those sublevels. So the 4S sublevel is actually slightly lower in energy than the 3D, and it is ever so slight, but it is lower in energy than the 3D sublevel. Now, we have to remember that when it comes to writing our electron configurations, but there is an easy way of us using the periodic table to figure that out. So, bear with me. If we look at the periodic table, the periods, so the ones going across, they represent the main energy levels. So we've got the first main energy level with hydrogen and helium, we've got the second main energy level with lithium through to neon, and then the third main energy level from sodium through to argon. And yes, then it does get a little bit complicated because then we have the 4s and the 4p, but we have the 3d in the middle, but you get the idea. We've then got for period 1, 2 and 3, we have 2 elements, which is the 2 electrons that we can put into an s orbital. So hydrogen with 1 electron would have a configuration of 1s1. Helium would then be 1s2. When we then move to lithium, because we've come down into the next period, lithium would be 1s2, 2s1. Now you can figure that out just by counting or figuring out, first of all, how many protons a particular element has, which will tell you how many electrons there are in atoms of that element. And then you can kind of go, right, well, the first S holds 2, so 2, I've got 14 minus 2, I've got 12 left. So then I can fill the 2s, which will be another 2 electrons, that takes me down to 10. I can put 6 in the 2p, which means that I'm going down from 10 to 4, and then I can put 2 in the 3s, taking me down to 2, so I'll have 2 in the 3p. And that isn't wrong, that's absolutely fine to do. But if we just follow through the periodic table, we can see that those 2 elements there represent the 1s, so 1s1, 1s2, 2s1, 2s2, 2p, 1, 2, 3, 4, 5, 6, 3s1, 2, 3p, 1, 2, 3, 4, 5, 6, And here's the really nifty bit. When we then come down here, we're at 4s1 and 4s2, then we go to 3d10. And that's the one where the 4s actually fills before the 3d, because the 4s is lower in energy. And if we follow through the periodic table, the 4s1 and 2 come before the 3ds, which is quite handy. So then 3d 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 4p 1, 2, 3, 4, 5, 6. And you will only be asked up to krypton. So we only need to know for 36 electrons how to sort that. So I think that's a lot easier, because when you find whichever element it is that you want to do, so I'm going to do 3 examples here with you, the first one being fluorine. When I find fluorine, I know that it's going to have a configuration that includes the configuration for hydrogen and helium and lithium and beryllium and boron and carbon and nitrogen and oxygen, and then be one further along, if I'm making sense. Probably easier with some examples. So for fluorine, we have got the 1s2, fluorine's after that, so fluorine will start with 1s2. Then for the lithium and beryllium, fluorine still comes after those as well, so then we'd have the 2s2, and then fluorine is in the p block, and it's therefore going to have some electrons in the 2p sublevel. And how many is it going to have? 1, 2, 3, 4, 5. And that would be fluorine's electron configuration. Now, of course, knowing that it has a proton number and therefore 9 electrons, we could have, as I just tried to illustrate with silicon, kind of go, well, I'm using 2 in 1s, so 9 take away 2 means I've got 7 remaining. Okay, so I can put 2 into 2s, and then we can move on again, and that leaves me with 5. Okay, it's 2p5. But I just think that if you know how many electrons can go into each orbital, and you know how many s orbitals there are, 1, how many p orbitals there are, 3, and how many d orbitals there are, 5, that this sort of way of following it through the periodic table is a bit easier. And it probably seems not that much easier for fluorine, but as we work further through the periodic table towards elements with higher atomic numbers, which we'll do now, hopefully you'll see the benefits. So the next one we're going to do is manganese, which is here in the D block. So manganese's outer electrons need to be in d orbitals. So again, I could start with 25 and figure out the maths of how many electrons go in each subshell, or again, I can follow it through like I just did with the fluorine example. So we're starting off with 1s2 for the hydrogen and helium, then we're coming back to 2s2, and we need to keep going because we're not at manganese yet. Then we've got 2p6, and then we're going to keep going. Then we get to 3s2, then we keep going. Then we get to 3p6, and we have to keep going. Then we get to 4s2, and then manganese is there. So we're going to have electrons in the 3d. How many are we going to have? 1, 2, 3, 4, 5. Job done. And I'll do one more for good measure. Next one we've got is As, which is arsenic, which is here. So we know that arsenic is going to have the same configuration as the manganese, because arsenic comes after the manganese, but we need to make sure obviously that we kind of fill the 3D up before we move on to the P block. But that's, you know, kind of a bit of a cheat we can do here, because I've already done manganese. We can say that it'd be the same up to the 4s2, then we would have the 3D and it'd be full with 10, and then arsenic is here, so then arsenic would end with 4p1, 2, 3. But I'll do it again in full one more time so that you can see how I'm doing that, and then hopefully with those examples you can maybe give this a go. So arsenic is there. So we've got to get through all of that part of the periodic table first. So we're going to start, as always, with the 1s2. Then we've got the 2s2. We've got the 2p6 for that little part there. Then we come back into the third main energy level and we have 3s2. Then we have 3p, 1, 2, 3, 4, 5, 6, 3p6. Then we have the 4s2, which fill before the 3d. got to go all the way through there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which if we know that there's 5 d orbitals and each orbital can hold 2 electrons, 5 times 2 is 10. And then arsenic is here, so 4p1, 4p2, 4p3. And hopefully that's made life a little bit easier for us. Now, if we were then thinking about ions, we would need to have a think about whether electrons had been lost or gained, and you can always start by writing out the configuration of the atom and then making changes depending on what the ion would be. So because fluorine's in group 7, we're going to make F- ions, so that means an electron will need to be gained, and it would be gained into here to give it a 2p6 configuration. Now, we know that elements want to gain or lose or share electrons so that they have full outer shells, and the noble gases in group 0 already have full outer shells. So when fluorine gains an electron and becomes 2p6, it has the same configuration as neon. It has a noble gas configuration, and the F- ion is much more stable than the fluorine atom would be. Hopefully that's made utilising the periodic table to write electron configurations a little bit easier. As always, any questions, please let me know. And if you want to have a go at some, pick any element that you want to between hydrogen and krypton. We don't need to go any further than krypton. And then, yeah, find an element, work it through. And if you want me to check it, just let me know. Hopefully that's been helpful, guys. I'll speak to you soon.